All right. So let's talk about process synchronization. So I had you guys look at what I give you, 3 or 4 questions, and most of them dealt with what signals, and did I have a semaphore one in there? Did I have a semaphore or not a semaphore? You would think a crazy name like that you guys would remember, right? I chose not to ask Levi. It was a 50-50 shot. Did you do the homework? Oh, yeah. Your default answer just becomes no, and then you upgrade if necessary. Is that the All right. So let's talk about process synchronization. So in general, what does it mean to synchronize processes? What are we trying? What are we talking about there? We've kind of already mentioned it in here, for several times. But what does that phrase mean? Process synchronization. What?
Aren't you trying to basically eliminate overlap when two processes running at the same time?
Okay. What are some reasons why we'd want to take away that overlap? Let's give some definition to overlap.
There was a specific term in that. If my time, I can't remember it.
Well, regardless of what like a specific term might be, just what are, in general, if we take this into real life, what are some things that can happen when we have more than one person working on the same task or related tasks, for example?
They could need access to the same data.
Okay, so we might need to control access to a resource, right?
So processes might overwrite a variable that shouldn't have been changed because it was already changed.
Okay,
I
so
can't remember the term for that.
yeah, so
Condition? Is that the term?
well, so one thing, let's keep it in real life here. So let's say that we're 3 people are moving out of their apartments into one apartment. They're going to become roommates, okay? And one person has a truck, and they need to have the truck to move crap from there to the place. So only one of the people can use the truck at once. So that's a shared resource that has to have a lock put on that when it's being used by one of those people. Because that resource is not available to the other 2 to move out of their apartments until the first guy is done making the trip, right? Relatively common problem, right? Something along those lines. But now take we've used in the past the example of like cleaning up a park, where we can divide that task up, across multiple people. Now, is that something that do we need to control access to the park by to the number of people that if we have 8 people who are cleaning up the park? Does each one have to wait for the other one to be done with their part of the park before they can start their part of the park? Or does that kind of defeat the purpose? Defeat the purpose. Defeat the purpose. That breaks it, right? The whole punchline of splitting the job up is so that everybody can go into the park at once and start cleaning and get the park cleaned up more quickly. Okay, so that would be an example where we don't need to synchronize a resource. We don't need to control access to the resource, or at least the limiting the number of people that go into the park at once is going to be some big number, right? Like when you go into restaurants or bars and they say maximum capacity is, 125 people or something like that, when you know that sometimes there's more than 125 people in there. And there's also a cover charge, and that's when you see the YouTube videos of like balconies falling and stuff like that, right? You've seen those, right? Yeah. It's all because of people didn't listen to the fire marshal. Said, don't put that many people in here. Building will collapse. What was I talking about? Oh, okay. So basically the punchline of process synchronization would be getting multiple processes communicating with each other so they can all be on the same page. Okay, so they can synchronize their intent with each other. Sometimes that means one has to wait on another one. Sometimes that means that they just know when each one is done with their particular task, but they're not really waiting on another person. That's kind of the observer design pattern, right? We can have two processes that ultimately have the same goal, but they can't kind of meet up and do that. So, maybe the three people who are moving into the apartment together, once all of them are moved in, they're going to come together and go and sign the lease paper or something like that. It's probably a chicken or the egg type problem, but you get what I'm getting at, right? Okay, or they're going to go pick up keys or something like that, or get the keys copied. Yeah, that's a good one. Get the keys copied. All right, until they've all moved in. So they can each independently do part of the move-in task. We've decided we're going to control access to one resource, that's that moving truck. But every one of them could be at their current apartment packing up boxes, stuff like that, getting it staged maybe in the front yard, kind of ready to load onto a truck, that kind of stuff. Ready for that truck to become available so that they can get to work as quickly as possible. But once they've all notified each other that their task is complete, that's when they can go and do the next thing that requires all of those things having come together. That's where synchronization comes in, that type of stuff. So it all comes down to communication, and it's not a foreign concept to us. We deal with it all the time in real life. But we give a funky name to it in operating systems because it makes it sound smart, right? Most smartest, actually. Which? More smartable? Is that what you said? Or that's not what you said, but that's what you wish you said. It's that one? More bestest. Most bestest. Most besterable. Got it. Okay. So, Peterson solution? That's got to be made up. So in any case, I didn't give you a question on Peterson's solution, did I? There was a couple of questions on Peterson's solution. I looked at them, and I think I spit at the book. I hate algorithms that are just named after people. And then you read it, you learn about it, and it's just something stupid, like obvious.
You tried to get one named after you, and they wouldn't do it.
And I hold a grudge. I do. I hold. It was the Lippmann recursive algorithm of everything. Okay, kind of what was Einstein was looking for a theory of everything, right? So this is the recursive algorithm of everything. Christian worldview. That's right. Exactly. Okay, so let's kind of dive in here. We just covered the what's this guy? Whatever. It's just dumb. All right, so this is producer consumer problem in general, which we've kind of already talked about before. But sometimes you have things that get produced, and then you have things that get consumed. So, for instance, we all go to the grocery store because that's where the soda lives, right? So the company produces the soda, puts it into one centralized place. We all go to the grocery store to buy the soda or steal the soda. I don't know what you guys are doing these days. It probably depends on the time of night. But the punchline being that this is kind of a normal cadence of things. And the grocery store is going to be a resource that we are sharing. And for instance, when you go to the aisle where the soda lives, that's a depletable resource. So as you use that resource, now there's less cases of soda available afterwards. All right, so idea of a race condition. All right, so me and Schumacher, we get to the grocery store at the same time. We've already covered the incredible foot speed that we're sporting over here. Okay, that's why I do the reverse sprint stuff. Did you miss that part? Were you not paying attention at the beginning? When I say I sprint in reverse, but I don't do the little back pedal thing, I do full stride. You got that? Okay. Yeah, it takes incredible quadricep flexibility, which I don't have.
I thought you were just going to ride that horsey for 1 second.
The who?
The horsey at
Oh, I tried to ride it once. Did I tell you that?
Yeah.
Yeah, no, that was a true story. They told me to get off. Should sue those people.
They do have an age limit.
No, there's not a published age limit there. You think there should be, but there's not.
Now there is.
You broke the horse's legs. You did what? It was a mechanical horse. We had to put her down. All right. So in any case, so you and I, we both walk into Meijer at the same time. Okay, and we're gonna go at a sprint to the. You like Diet Coke, right? Yeah. All right. We're going. Is it Coke or Pepsi? Diet Coke. Okay, we're going for the Diet Coke. I prefer Coke Zero, but whatever. I mean, I basically will compete with anybody over anything. Is what it comes down to. So we're making a mad dash for the Diet Coke. We both get there at the exact same time. One case of Diet Coke left. All right, who gets it? Probably in that scenario, I get it. Okay, for like all sorts of reasons. Probably him just not being aggressive like that, and the other one is I could just kind of go dead weight onto him, and legs break and all sorts of things. And he's crying, and I grab the Diet Coke and I leave. But punchline is in a computer system where we have some resource that should only be usable by one person. This is the best example of something like this. We want to ensure that that resource can only ever be grabbed by one person. Okay, so in our supermarket example, we're going to say that there's some sort of bouncer protecting the one case of Diet Coke. It's the last case of Diet Coke in existence. All right, and it just so happens that this is like the book, Ready Player One. Right, the two people were racing for the end goal thing to solve the puzzle.
Spoilers. I guess.
You read it, didn't you?
I did read it, but the ending I remember is the guy comes.
Okay. Is anybody else reading that book?
I love that book. I've read it twice.
You got to read it. It's a really good book.
It is. I literally have read that book.
Yeah, then I gotta read.
What is this?
It's
What's
on
what?
Fallout 4 dialogue.
What is that cup?
Oh, I left the keg at home.
Well, you better go get it. That's no excuse.
I hadn't finished the coffee from yesterday, so I have it on ice. I'm going to bring it with me to my grad class tonight. Plus I actually have found it's really good. It's a really good mug for the hot tub because it floats. The lid is airtight, so I can just put it in there and it literally floats around and it keeps the coffee warm.
So it literally is like a cake, like a sealed cake.
Yeah. That thing got me through like 4 episodes of The Flash yesterday.
I was going to ask if you watched it yesterday. But
No, and actually that's one thing I'm upset about is I'm just about done with season 1 on Netflix. And I've set it up to start recording it on that it's on TV now. But I think it was episode 7 of this season. So I'm missing episodes 1 through 6.
Big problem.
Huge problem.
You can watch those
yesterday.
Huh?
It's available on the
It recorded an episode yesterday or 2 days ago. Is it available? Well, is it legitimately available on the internet or is it just available on the internet?
You can go to the.
stream it and like,
You just but they typically only have the most recent 3 or 4 episodes, so you probably missed the first couple.
So I need to switch over to it's available on the internet version. So some sort of torrent or something like that.
you don't even have to stream. You just stream it. There's plenty of sites. So you just stream.
Yeah, but I don't want to watch it on a computer. I want to watch it on the big screen. So then I have to download it and convert it. And
Just pay like $40 a year for a VPN and then torrent everything.
Well, no, I would have to jailbreak the Apple TV on the my big. I have my.
You can't just like play a thing from your video file from your
Computer? Yeah, I can through Apple TV. Is that all it does? Is it just acts like it's a video file that's sitting there and it?
If you torrent a video file, just like half the video file.
Oh, so torrent into my Mac and then do a screen share to the Apple TV. I probably could do that. But it's hard to use the remote, my phone while in the hot tub. It's the
First world problems, man.
first world problems.
Yeah,
That's
there
what you
go.
need is a life-proof case. Waterproof case.
No, I have one, but even when your hands are wet, it doesn't work right on it.
Oh.
Yeah, it thinks you're like this is gonna come off creepy. It thinks that you're touching it like in a zillion places.
Just keep it in your keg.
Just float it.
Yeah. and then you can take it
So
out.
when you're in your hot tub, it thinks you're touching it in a million places.
Exactly.
Okay.
All right. So, anyways, back to our Diet Coke example. So in a race condition type type situation, there would be some sort of bouncer at Meijer standing between you and I and the Diet Coke. And that guy then ultimately makes the decision who gets the Diet Coke. Okay, and a race condition occurs when we both arrive at the bouncer at the seemingly the same time. And that's more probable today than ever before. Now that we have all these multiple processors and multi-channel interstates, communication channels between the various resources on our computer, there are legitimate circumstances now where two things could arrive at the exact same time. And I use quotes around exact same time, but only barely today. I mean, you could potentially have two things that basically show up at the same time. So that bouncer now has to make a decision. Okay, who is going to get the Diet Coke? Is it going to be the morbidly obese guy who obviously needs it? Or is it going to be the skinny dude?
Use bribery.
Clearly he's going to give me the Diet Coke. All right, so, but the punchline is that's a race condition. Okay, the bad side of a race condition is if the bouncer isn't able to multitask, and instead we both arrive at the same time, and he lets us both in. He thinks we're both there first. So now we're both past the bouncer, and we both, in real life, we can only physically leave with, only one of us can leave with the case, right? The case is, it's encased in titanium, so we can't rip it and have cans everywhere. So we're going to say that's the case here. Well, it's an all or nothing type situation. So in real life, this problem is solved. But in a computer, we potentially could both grab the Diet Coke. We both walk out the door with a case of Diet Coke, even though there was only one case of Diet Coke. Make sense? That's a problem. All right, so that's what a race condition is. So they're doing it based on some counter that they're incrementing, it looks like. But whatever this code does, what I just explained is an accurate representation of race conditions. Okay? So we want to be able to protect against that. We need to have some sort of way for that bouncer to make it an impossibility for both of us to get past him. That one of us is going to get blocked. One of us is going to arrive a fraction of a microsecond first, or even if we do arrive at the same time, there's some sort of real-time coin flip that decides which one of us gets it. Somehow. Okay, that prevents more than one person to getting access to a resource of which there's only one at the same time. Okay, so they're talking about a critical section problem. So each process has a critical section of code, kind of important part of the code, something you would not want other things to be able to go in and trash. So critical section problem is to design protocol to solve this problem. Each process must ask permission to enter the critical section in any in an entry section. So may follow critical section with exit section and remain. That's just stupid. Okay, so punchline is that a particular process might have a secure vault in it. Okay, a place where it keeps important parts of that process, and other processes have to ask permission in order to get into that vault. And a process then gets to decide who has access to the vault based on what are they going to do with it. Take it to a less operating system-y example. If you have a variable in Java or something like that you want that 10 other objects need to have access to, as long as they're not going to change that variable, we don't care how many people have access to it, right? But if that variable is something that gets changed, that value is something that's going to get changed, well, we now need to control, at the very least, how it gets changed. We might allow anybody to have read access to it. But a second somebody wants to write to it, now there becomes a cadence. Okay? We can see this in real life for those of you who use Dropbox. Let's say you and I are both, we have a shared Dropbox folder. We've both opened up a Microsoft Word document from the same Microsoft Word document from Dropbox on different computers. Okay? We're both working on it locally in our computer. As soon as we double click on it, it loads the current version of that document into memory. Now, a lot of our web browsers today are kind of aware of the cloud problem. So sometimes they'll give us a little warning saying that the file on disk is out of sync with this file or something like that. But let's just go back to the days where that didn't exist. So now we have the issue where we're both working on the file. We both made a bunch of changes to it. I hit save, which puts my changes to Dropbox. And then a minute later, he hits save, completely overriding my changes. My changes are now gone. Okay, because it was whoever saved last wrote to that. That's the problem. So writing, making modifications to a value is a problem. We don't care how many people open up that Word document locally on their machine as long as they're not going to change it. Okay, so read access is a whole different scenario than read write. All right. All right, so kind of this chart here, we just think about how does the critical section work. Let's again take this back to a real life example. When you go to the doctor's office, you check in at the front desk, they put you in the waiting room, and they tell you when it's your turn. Okay, you don't get to run back to the operating room. All right, being the critical section, right? Somebody else might be currently using the operating room. That's critical section. All right, we're going to wait in the waiting room. That's our entry section. Somebody's going to come and get us, invite us into the critical section, and then if there's something that needs to be done on the way out, maybe we need to turn in the key or something like that, that's the exit section, and maybe these guys are linked to each other. So maybe there's only one key, for example, and once we turn that key in, it's now available to invite the next person in, kind of controlling that cadence. You know, when you go to those gas stations that have the, the key on the stick to the bathroom, kind of prevents more than one person to go into the bathroom. Unless the other guy lets him in, that just becomes creepy, So in any case, that's the critical section problem. All right, so I would say in your mind you should forget about this phrase critical section problem. Okay, just think about what we just talked about. Think about creepy guy in a bathroom at the gas station. Well, I guess two guys in that example. All right, so we have so we have various ways of solving this problem. So we have mutual exclusion. So if process P is executing in the critical section, then no other process can be executing in their critical sections. All right, so mutual exclusion says nobody else has access to it. Okay, mutual exclusion also. So a mutually exclusive problem would be a problem where two entities or more than one entity are working on something that has nothing to do with something else. All right, so the problem itself is mutually exclusive. But now when we're dealing with mutual exclusion in terms of access to a resource, when one person's accessing it, it's off limits to anybody else. All right, that would be the ideal situation, the ideal solution if we only have one resource to share. All right, progress. If no process is executing the critical section and there exists some processes that wish to enter their critical section, then the selection of the processes that will enter the critical section next cannot be postponed indefinitely. And this has to do with almost like a scheduling problem. All right, who gets the key to the bathroom at the gas station first if two people run in? Okay, probably the guy with the stomach problems, not the guy who just has to pee. Something like that. All right. So something along those lines. Bounded waiting. A bound must exist on the number of times that other processes are allowed to enter their critical section after a process has made a request to enter its critical section and before that request is granted. All right. So now, what's the example that they're using here? So with the bounded waiting, this deals with, and this is where the critical section part comes back in. I'm a process. I have my vault over here. Now, sometimes external processes need access to the vault. Now, the problem is that sometimes I also need access to my own vault. Now, in a situation where changes are going to be made in that vault, we might say that I should have high priority for making changes to my own variables, right? Rather than the external people who I've decided to trust to make changes to the variables being higher priority. But at some point in time, I'm still sharing my own vault with other people, all right? And there has to be some sort of governance around When am I allowed to access the vault? How many other people can access my vault in the interim between my own requests? That kind of thing. All right. Oh, very interested in Peterson's solution to this. Okay, the two-process solution. Assume that the load and store instructions are atomic. Okay, well, let's talk about atomic real quick. So, atomic instructions, think it's a magic trick on the CPU. So an atomic magic trick on the CPU means it's something that happens exactly one CPU cycle. Right? And that's an important thing because nothing can interrupt a CPU in one cycle. So if we have multiple CPUs that are doing things, or even one CPU that gets interrupted, if there's a process, if there's a magic trick that's being performed, and it's a 10-cycle magic trick, takes 10 individual hand waves by the CPU, then it could potentially be interrupted mid-magic trick. Make sense? And during that interruption, we might have a point in time where somebody else could grab a resource. Kind of bringing it back to this resource example. But in atomic instructions are non-divisible. We could never, it's impossible to interrupt a CPU in the middle of executing a magic trick that is atomic. That means if we can put in atomic instructions, an atomic bouncer, okay, where the bouncer never takes his eye off the ball. It's impossible for the bouncer to take his eye off the ball because when he looks, when he's deciding who gets access to that resource, it literally takes one cycle. The minimal amount of time it could possibly take. Okay? So that's what an atomic instruction is. All right? So assuming the load and store instructions are atomic, that is, it cannot be interrupted. So kind of what I just said. The two processes share two variables. Maybe they share a variable called turn and another variable that's a two-bucket array of type Boolean called flag. Okay, so the variable turn indicates whose turn it is to enter the critical section. All right, so turn might just be the ID flipping back and forth or something like that. The flag array is used to indicate if a process is ready to enter the critical section. So flag at bucket I is true. It implies that the process I is ready to go in. Okay? So if you and I are two processes, actually we'll go back to the victory I've already won. He's a little stockier than you, so there's concern there is what I'm saying. And plus former football player knows how to hit low and stuff. I think you would fold. I'm just saying, I call it the way I see it. All right. So in any case, you and I are we're back to this Diet Coke war, right? Okay, so we're back to the Diet Coke war, and we have this bouncer is built around two variables. Okay, whose turn it is, except in this case, we're not stealing the whole case of Diet Coke. We're alternating, grabbing cans of Coke, and it's a chugging contest in this case. All right, I've decided to be nice and share. But I also think I could probably drink it quicker than you can. So I'm going to be ready for that resource more often than you are, which again is sad. So we have these two variables, turn and flag. So turn decides whose turn it is. And then, so this two bucket array is for two processes in this case. So maybe I'm looking at bucket 0 of that guy. You're looking at bucket 1. So I'm process 0, you're process 1. And whenever bucket 0 is true, that means I have access to the resource, okay? Assuming flag says it's my turn. Okay, whenever bucket 1 is true, that means you have access to the resource, assuming flag says it's your turn. All right, so the variable turn indicates whose turn it is to enter the critical section. All right, so ultimately, this is the green light. Right? So there's kind of two levels of this. One level is we're only even allowed to consider whether it's our turn if flag says that we are allowed to have access to it. Okay? So where does it say what flag is? Flag array is used to indicate if a process is ready to enter the critical section. So if you're still drinking your soda, okay, your flag is going to be set to false. All right? But if I'm done drinking the soda, my flag is going to be set to true. I'm ready for that resource again. Okay? But I still have to get through the bouncer. Turn, in this case, is the bouncer. Okay? Now, turn that bouncer, in order for this to work correctly, is going to have to be atomic. All right, so talks about the two things. Here's the turn variable, and here's the flag variable. So here's the algorithm for this. So this is for process P of I. So maybe this is me. So I've decided I finished my first can of soda, and I'm ready for the resource. So I set my flag to true. I'm ready. Then I set, do we get what J is here? All right, so this is the bouncer's algorithm. So the bouncer is going to go ahead and say that flag at bucket I could be ready. And then he's going to set whose turn it is to J. And then while flag at bucket J, the person's turn, okay, while this guy's turn is true and it's currently his turn, go ahead and let him at the Diet Coke. All right. So as long as I'm ready for the Diet Coke and it's my turn, the bouncer's going to let me in. As soon as I'm done, the bouncer's going to flip false to true, the true to false, saying I'm no longer ready. I now have a can of Diet Coke. It's time for me to go and drink the Diet Coke. Okay? And it's going to just do this forever. All right, so this is the, nothing in here says this is atomic yet, so I'm assuming they're going to give us, there's all sorts of bad things can happen in here. So let's just keep trucking. So this says this is provable that mutual exclusion is preserved. Progress requirement is satisfied. Bounded waiting requirement is met. So how is mutual? So the critical section is going to be a set of code. So this is the grab the can of soda and run out the door code. So once the bouncer lets me by, I'm going to go ahead and grab a soda from the case and I'm going to leave. So this while loop doesn't complete. This while loop does not, well, actually, hold on. This while loop is a busy wait while loop. That's a semicolon there. So this is going to say it's J's turn, whatever J is. So J in this case is the current guy. So this might be me. So J might be 0. I in this case is also 0. So I'm ready and it's my turn. So as long as those things remain the same, sit there and just wait, blocking anything else from getting in here. Okay, so we basically have the bouncer. So this while loop in this case is the bouncer. He's using these two separate variables to block the door because somebody's already inside grabbing the Diet Coke, right? Because this is not the code that happens during this while loop. Instead, this is a busy wait while loop. That semicolon is there. So this just says keep sitting here and spinning, keep blocking as long as both of these variables remain I guess these values. So as long as J is still ready, and as long as it's still his turn, we're going to let him stay in there. All right. Then as soon as I say, okay, I have the Diet Coke, and I flip flag at my bucket, flag at bucket 0 back to false. I'm not ready anymore. This is going to fail the very next time, right? It's going to fail the next time because doesn't matter whose turn the bouncer thinks it is, it's going to say this guy no longer needs the resource. He's out. So I'm not going to flip that back until I exit the critical section. All right. So then the bouncer is going to go ahead and reset his flag array and get out of there. All right. And then if I want to do something in the waiting room afterwards, I can, because that's not part of the critical section. I can hang out looking at the soup aisle at Meijer while I'm drinking my Diet Coke if I want. That doesn't have any impact on accessing that case of Diet Coke. So the question is why is that guaranteed? Because this is not an atomic action, or rather, this is not an atomic action. This is not an atomic action. Both of those things, I mean, that's by definition, right? We know that, you know, that a high-level language has a one-to-many relationship with the CPU. So every line of code in here potentially is equal to many lines of code on the CPU, right? So setting this variable equal to this value is going to involve several lines of code. We have to resolve this value. Then we have to set this variable equal to that value. That's going to involve moving some, you know, temporarily storing something in a register, then temporarily storing the memory address of turn in another register, and then moving the value from this register into this register. Several steps, minimum of 3 or 4 steps, let's say, something like that. That is not atomic. All right, same thing's true here. This guy is probably atomic, just the value true. Okay, so we wouldn't have to resolve this, but we're still going to have to resolve the specific memory address that is flag at bucket I. That's going to be we have to resolve the base address of flag, then offset off of that to bucket I of that guy. Store that now new target address inside of a register somewhere, and then ultimately put true into that value, into that memory position. Okay, so not atomic clearly. Not atomic clearly. So why would they say this is atomic, or are they saying that's atomic? Because checking this is not an atomic action. Checking flag at bucket J is going to involve resolving flag, then offsetting to J and grabbing that value, whether it's true or false. Then we're going to apply the AND. So by definition, this is at least 2 things, right? With an AND, at least 2 things are happening. So by definition, if AND is involved, this is not atomic. So we need something else to block it. Is there like a punchline to this? There's not. Is this Peterson's made-up solution? 2-process solution. Okay, so we're limiting this to 2 processes. Let's see if that makes a difference here. Limiting this to exactly 2 processes. So our example where it's me and Nick fighting is fine. We assume that, that's the issue here. We're assuming that load and store are atomic. So basically they're giving us a high-level code algorithm of this, but realistically it's a single magic trick to load a variable and a single magic trick to store a value. This is a pretty big assumption here. Atomic load and store, but it would still have to be written in a low-level language. So what they're saying here is that this line is atomic because they've said assume it's atomic. This line is atomic because they've said assume it's atomic. They don't say resolve. These would not be atomic in here, but it doesn't matter since these guys are atomic. So changing these would literally happen inside of 1 cycle. There's nothing special about this algorithm. This is just our bouncer. Process is readied. No. Promise you, I will not ask you about the Peterson solution on the final. It's just such a... No, the correct solution to this type of thing is using a semaphore, not 2 arrays to do this. All right, so we'll get to that. Let's see. So synchronization hardware, so now we can have physical pieces of hardware instead of a software solution for controlling access to a resource. So many systems provide hardware support for critical section code. So we can have a uniprocessor, which could disable interrupts. So now the processor while something is working on a critical section, it does not allow that something to be interrupted. It gets the CPU time till it's done. So currently running code would execute without preemption. Generally too inefficient on multiprocessor systems. So, you know, because we have to make a kind of a guess how long is it's going to take, how long it might take to run in the critical section. So anywhere between 2 microseconds up to a day. Depending on, we probably don't want your CPU sitting there working on a certain problem in the critical section for a day without any interruption. So uniprocessors might make decent sense from that perspective if we just disable interrupts on a single core processor, but probably not from a user's perspective an appropriate solution. Okay? We want to protect that, maybe from a user's perspective, we don't mind if the critical section is protected as long as our end user experience is not reduced. Okay. Modern machines provide special atomic hardware instructions. So again, this all comes down to this idea of atomic things that can happen in a single CPU cycle. So atomic effectively means non-interruptible. It happens either, and actually that is a true statement. What I've been saying is atomic means something that happens in one CPU cycle. That's not 100% true. We could say that atomic is something that either happens in one CPU cycle or happens as if it were done in one CPU cycle, which means that this non-interruptible is probably more accurate. All right, so if the CPU does some sort of cannot be interrupted in the middle of this magic trick, even if that magic trick takes 9 steps to accomplish, if it's turned off interruption during that, it's as if it happened in a single cycle, because the CPU can't be interrupted in between. So we either test the memory word or set a value, so that's the load and store thing. So we might have a specific hardware that allows us to set a circuit or read from a circuit in real time, or swap the contents of 2 memory words, again in real time, uninterruptible. Okay, so we'll stop there. How close are we? Oh, yuck. All right, so we will start on this slide next time talking about locks. So this has got to be getting close to semaphores, which are kind of the right way of doing this. All right, I will see everybody on Friday.